Hey guys, I'm Zarina Begum from CCAP Institute of Engineering and Technology. Today in my video, I will explain the Big M method. Big M method is also called as the penalty method. The Big M method is an extension of the simplex method. This problem is of type maximization, and these are the three constraints for the given problem. To solve this problem, the first step is we have to convert the given problem into standard form. To do this, we follow three rules and find out whether my constraint is of type less than or equal to, greater than or equal to, or equal to. So if it is less than or equal to, I add the slack variable. If it is greater than or equal to, I subtract the slack variable and add artificial variable. If the constraint is of type equal to, then I add the artificial variable. Let me take the first constraint. As the first constraint is of type less than or equal to, so I add the slack variable. The second constraint is of type greater than or equal to, so I subtract the slack variable and add artificial variable. And the third constraint is of type less than or equal to, so I add the slack variable. And I reform my objective function. So the coefficients of S1, S2, S3 we keep as 0, and the coefficient of the artificial variable is minus m for maximization and plus m for minimization. Then we solve the given problem by using the simplex method. So to do this, I form an initial table, and the first column in this table is basic variable. Basic variable are those variables which we have added into the constraints. So it is S1. I will not consider S2 because it is having negative sign. So my next basic variable is A1 and then S3. So coefficients of these variables in the reformed objective function is 0. For A1 it is minus m, and for S3 it is 0. Then I write down all the coefficients of these variables in my constraint equation. So it is 2, 1, 1. So S2 and S3 is not there in the first equation. Then this is 1, 3, 0, minus 1, 0 and 1. Then we do not have x1, so it is 0, 1, 0, 0, 1 and 0. Then the next step is to find out Zj. Zj is nothing but summation of Cb into Xj. So it is 0 into 2 plus minus m into 1 plus 0 into 0, which is nothing but minus m. So I write down minus m. Next, it is 0 into the x2 value is 1 plus minus m into 3 plus 0 into 1. So it is nothing but minus 3m. So minus 3m. Similarly, I perform the same operation for this particular values. So it is 0 and then it is m, it's 0 and minus m. Then we find out the delta values. The delta value is nothing but Cj minus Zj. So for this particular column, the delta value is Cj minus Zj. Cj value is 3 and Zj value is minus m. So 3 minus of minus, it becomes plus. So it is 3 plus m. Next, the next Cj value is minus 1. Minus of minus 3m, it is minus 1 plus 3m. Minus 1 plus 3m. Similarly, 0 minus 0, 0 minus m, 0 and 0. Then, to check the optimality and to find out whether this solution is the final solution or no. So what do we do? For the maximization problem, to reach optimality, all of my delta value should be 0 and negative. So, but we have not reached 0 and negative values. Still few of my values are positive. Among this, I select the most positive. M and 3m are among m and 3m, the most positive is 3m. So I select this as my key row. Then correspondingly I find out the this is the key column. Correspondingly, I find out the key row. And my b values are nothing but whichever values we have at the right hand side of the equation. So it is 2, 3 and 4. So the theta value is b divided by key column elements. So 2 divided by 1 equal to 2, 3 divided by 3 equal to 1 and 4 divided by 1 equal to 4. So I name this row as R1, this as R2 and this as R3. Among these, the least positive value is 1. So I select this as my key row. Okay. So intersection of key column and key row, we have got the identity element. And always your identity element should be 1. If it is not 1, then make this as 1. To make this as 1, I divide this element by 3. Similarly, I have to divide the entire row, that is R2, by 3. So my next operation is I divide this. So I make the next iteration over here and I get the values. So this is the next table. So I name this rows as R1 dash, R2 dash and R3 dash. So I have to perform the operation for R2. So R2 dash is nothing but R2 divided by 3. Meanwhile, your entering variable will be x2 in place of a1. So in a1 I replace x2 and I take down its coefficient, it is minus 1. Similarly, s1 and s3 I keep as it is. Then I perform the operation. So these are my values. So there is no need to calculate a1 because it is already leaving the table. Then you can just cross it and 3 divided by 3 will be 1. Then the elements above your identity element or below your identity element, these are called as corresponding elements, and always your corresponding element should be 0. If they are not 0, then make them as 0. So to make now my corresponding element is 1 and identity element is 1. So I subtract the corresponding element with this. So 1 minus 1 will give me 0. So my R1 dash is nothing but R1 minus R2 dash. So when I do that operation, I will get the values. So it's nothing but 2 minus 1 by 3, then 1 minus 1, then 1 minus 0, 0 minus minus 1 by 3, and then I have 0 minus 0, and no need to calculate this. Next is 2 minus 1. So I note down this values. This is 5 by 3. This obviously I want to make this elements as 0. You can write it down directly. Then this is 1. This is 1 by 3. And this is 0. This is 1. Similarly, this operation will be R3 dash is nothing but R3 minus R2. So when I do that, I get the values. So it is minus 1 by 3, 0, 1 by 3, 1, and 4 minus 1 is 3. Similarly, I find out the Cj values. Cj values are nothing but again summation of Cb into Xj. So it is 10 by 3, 0, 0, minus 1 by 3 and 0. So these are your delta values, 10 by 3, 0, 0, minus 1 by 3 and 0. This is minus 1 by 3, minus 1, 0, plus 1 by 3 and 0. Then check whether you have reached the optimality. Still I have not reached the optimality and I am getting still positive values. The most positive is 10 by 3. So similarly I follow the same procedure and try to mark this as the key column, and the key row values are 3 by 5, 3 and minus 9. Among this, the most positive is, so I mark this row as key row. So in my next iteration, I will have x1 as an entering variable in place of s1. So I write down these values in my next table. So in place of s1 I have x1. So x2 will be as it is, and this is s3. So this is coefficient of x1 is 3, this is minus 1, and this is 0. Next, my identity element is 5 by 3, but it should be 1. To make that 1, I have to multiply with 3 by 5. So I perform the same operation with all the elements. So my r1 double dash is nothing but r1 dash into 3 by 5. So when I do this operation, I get the values here. So I want to make this element as 1. It is 1 when I perform the operation, 0, 3 by 5, 1 by 5 and 0. And this is nothing but 3 by 5. And I have to make these corresponding elements as 0. So to make that, I perform r2 double dash is nothing but r2 dash minus 1 by 3 into r1 double dash, and your r3 double dash is nothing but r3 dash minus r1 double dash into minus of 1 by 3. So when I do this, I get the values 0, 1, minus 1 by 5, minus 2 by 5 and 0. Then next it is 0, 0, 1 by 5, 2 by 5 and 1. Then my zj values are 3, minus 1, 2, 1 and 0. And cj minus zj will be 0, 0, minus 2, minus 1 and 0. So let me check whether I have reached the optimality condition or no. So all of my zeros are negative, all of my delta values are 0 and negative, and 3 cases might arise at the end of your simplex method, and we have come with the case 1. That is, if no artificial variable remains in the basis, there is no artificial variable here, and when you have reached the optimality condition, we have reached the optimality condition where all of my delta values are 0 and negative, then your solution is optimal feasible solution. Okay, then I note down the corresponding values of x1, it is 3 by 5, and my x2, it is 4 by 5, and this is 16 by 5. So I write down z max is equal to 3x1 minus x2. So 3 into 3 by 5 minus 4 by 5. 9 by 5 minus 4 by 5 is 5 by 5, which is nothing but z max is equal to 1.